Hello, it's Stat 134, Lecture 37. So last time in section 6.4 we talked about covariance, which is expectation of xy minus expectation of x times expectation of y, and correlation, which is basically the covariance normalized by dividing by SDX and SDY. And we noted that if we have k exchangeable random variables that sum to a constant, then the correlation of n1 and n2 is minus 1 over k minus 1, which makes sense since if n1 is very large, n2 must be very small. And furthermore, if x and y are independent, then the covariance is 0 and hence the correlation is 0. But the converse is not true. If the correlation is 0, then x and y need not be independent. For example, if x is uniform minus 1, 1, and y is x squared, then clearly y is dependent on x, but the expectation of xy minus x, expectation of x, expectation of y is 0 because because x cubed and x are both odd functions, and so for example, the integral from minus 1 to 1 of x cubed is 0, and the integral of x from minus 1 to 1 is 0. So there you go. So today we're going to finish section 6.4 and start 6.5. We'll first review responses to the concept test and then look at properties of correlation and give an introduction to the bivariate normal. So we began by looking at a Poisson process where the time to the rth arrival is gamma r lambda. So the covariance of t1 and t3 equals 1 over lambda squared. To see this, there's a couple explanations. One was basically if you write t3 as t1 plus t2 by thinking of t2 as the time of the next two arrivals after the first arrival, then the covariance of t1, t3 is just the variance of t1 plus 0, because covariance of t1 and t2 is 0, because they're independent. And and that's just 1 over lambda squared. You could also do this using just the definition of covariance as expectations, but then you'd have to find all of the expectations that we have here, and doing it out this way, you can see that you also get 1 over lambda squared. So properties of correlation that are proved at the end of the lecture is, first of all, correlation is a pure number between minus 1 and 1. Furthermore, correlation is invariant to a linear change of scale, except possibly by a sign. So in other words, the absolute value of the correlation of xy is equal to the absolute value of the correlation of some change of scale of x and some change of scale of y. So that makes sense because, for example, if you're looking at the correlation between Boston and New York City temperatures, it shouldn't matter whether temperatures are recorded in Celsius or Fahrenheit, because those are linear changes of scale. And to see how you could possibly change sign, just consider y to be x versus y to be minus x. That will basically flip r across the x-axis. So r is 1 becomes r is minus 1. So, and then the third property is that correlation doesn't matter the order of x and y. Here are some correlations going from 0 to 1. And then we did a concept test where I asked you whether x1 to x9 equals 20 is an important and true identity for finding the correlation. And indeed it is, because x1 is the number of green marbles picked by the first person, and x2 is the number of green marbles picked by the second person. And both of those are hypergeometric with the same parameters, because remember, we want to think of this as unconditional distributions. In other words, x2 is not dependent on what x1 is. So, the chance that x2 is, for example, 5 is the same as the chance that x1 is 5. So, so then, of course, the correlation will just be minus 1/8. And if you wanted to find the covariance, you'd need to find the standard deviation of x1 and x2, which, again, you would use the fact that x1 and x2 are hypergeometric, and we know what the SD of a hypergeometric is. So then we began bivariate normal, and so bivariate normal can be created. It's a joint distribution of two particular correlated normals, and here is how you correlate the two normals. So you start with two IID standard normals, and you rotate the plane by minus theta, and that creates a new random variable called y, which is cosine theta x plus sine theta z, which is standard normal. So we showed that in lecture 30. Letting rho be cosine theta, which is a number between minus 1 and 1, you can write y as rho x plus square root of 1 minus rho squared z, which is standard normal. And so that brings us to our definition of bivariate normal. X and y are standard bivariate normal with correlation rho if they're created from IID standard normals x and z as above. So then we explored some basic properties of bivariate normal, namely you found that the correlation of x and y is rho, which it should be. We looked at a picture of this, and so basically you can think of the bivariate normal as having a joint density over the plane, essentially lying over this oval shape here. And unlike the uncorrelated bivariate normal, in which case the oval is round, here the correlated bivariate normal has a upward facing oval if rho is positive. You can also draw it two-dimensionally, so you should be looking at a football here. Here I'm making the standard bivariate normal. So x and y are standard normals. And then we found the expectation of y given x was rho x. So in fact, this line that I've drawn here, what's called the regression line, is in fact a line. It's called also the graph of averages, since for any given x, it's the average value of y for that x. And finally, we found the variance of y given x. So this is the spread of values for any given x, and it's spread of y values that you get for any given x. So so we found that in fact the variance of y given x has no dependence on x at all. It's just 1 minus rho squared, so it's a constant. And so so y given x is rho x plus square root of 1 minus rho squared z, which is normal rho x 1 minus rho squared. So That is an important property we'll use next time. Have a good night.